Hello, this is Brett from SurvivalComms, and today on the bench we have the Yaesu FT-4X dual band VHF-UHF analog FM transceiver. This radio is Yaesu's entry-level radio. I paid less than $100 for it from Gigaparts and had it shipped to me. It was free shipping as well. Now, I did not purchase this radio for myself. I purchased it for a friend of mine who, after 2 days of instruction, passed his amateur radio license for both his technician and general class licenses. For doing such, I told him I'd buy him his first ham radio, and here it is. So before I give it to him, I figured I'd shoot a little video of it, and we'll put it through some paces on test equipment and see just exactly how it performs. Comes packaged in a nice little box, and you can see here the transceiver is made in Japan. All the accessories are made in China. And this is a USA market radio. I would recommend that the individual interested in one of these radios download the owner's manual and use it as we go through the radio. It has the specifications, and also if you go to the file section here, you can download the software for free. Here's the meat and potatoes of what's included in the box. We have our manual, a battery, an antenna, a transceiver, a belt clip, a drop-in charger base, and a power supply. The battery pack provided is a 1750 milliamp hour lithium ion battery pack. The supplied antenna is a rubber duck variety, 6 1/4 inches in length approximately, and has a fair amount of flexibility. Here's the base of our supplied antenna, and as you can see, it's an SMA female connector, and it's marked FM 136 to 174 and 400 to 470 megahertz, and that is false advertising. And as surmised, the antenna's performance characteristics do not match its markings. And zooming in, we can see that it's not even resonant in the 2-meter amateur band. And at UHF, this is a swept range across the markings on the antenna. Focusing now on the US allocation of the 70 centimeter band, we can see that the point of resonance falls below the point that where we would be utilizing this equipment in this spectrum. The desk charger is a standard arrangement drop-in type charger base with a single LED and 3 charging contacts. It seems to be of reasonable quality. The plastic doesn't give too easily, and you can see our specifications here. Input of 12 volts at 1 amp gives you an output of 8.4 volts at 800 milliamps. Now we get to the radio itself. The radio seems to be of decent quality. The plastic doesn't give too much on it. The size of it is extremely compact, as you can see here. For example, this is a standard garden variety Apex speaker microphone, and you can see that it's about the same size as this portable radio. Weight on my scale with battery and antenna is 8 ounces. The radio, again, has an SMA male connection on top. It has 1 momentary contact button on the top. It has a volume on-off control potentiometer on top, which has a overmolded housing to provide impact resistance, which is a good thing. This side of the radio has your push-to-talk button and 2 momentary contact buttons on the side. On the opposite side, we have our speaker mic plug-in, and also where your programming cable goes, and it has a threaded retention for a speaker mic, and again, it has overmolded protection in the housing itself for that connection point. On the back side of the radio, we'll see that we have a metal frame, and you can see where the top of our battery is inserted into here. You can see where your belt clip is screwed onto the body of the radio, and that it does go straight to the frame of the radio, and our battery is retained with this spring-loaded catch down here. Watch us move that back and forth, and we have a gasket around our battery contacts to provide a degree of protection against the ingress of water. The ingress protection rating of the radio is IP54, which means that it will resist the ingress of dust that will affect its operation, and will resist the ingress of moisture from splashing, such as rain, etc., but will not withstand pressurized water or submersion. And at the front of the radio, we have a forward-firing speaker, we have a single-line display, we have a standard DTMF keypad with 4 additional buttons. Turning on our radio with the volume knob, you can see it tells us the voltage, and then we have a 6-line alphanumeric display. We're in memory mode. You got your VFO-A, VFO-B, your wideband FM receive like broadcast FM takes place in VFO-B.
Try our new barbecue shrimp, jerk chicken, or BLT.
Go back to memory. On the top of the radio, the orange button, that's a momentary button. Its only function is to make noise, is an emergency button, which when you press it down, it beeps at you and it steers the radio to your home VHF channel that you have set. Reset. Just turn it on and off again. Push to talk buttons on the side. Here's your monitor button. And this is your function button. Regarding the function button, it's nice that it's just a single large button. A short key press allows us to hit the monitor button again and set your squelch level, for example. Hit your push to talk, it saves the setting. A long key press allows you to step through your menu items. And if you want to change one of these menu items, you can just hit that button again for a short press. And you can see, for example, here you can change whatever your repeater offset is for the frequency of interest, and then go ahead and save that setting by hitting your push to talk button. To step around your frequencies is really easy. You can just enter the frequency directly with the keypad if you choose to do so. You can step up and down. In the ham radio portion of the spectrum here, you can see it defaults to a 5 kilohertz step. When you go to the commercial spectrum, it goes to a 12.5 kilohertz step. And you can actually program whatever steps you want and override that. The smallest step the radio is capable of is 5 kilohertz steps, and the largest is 1 megahertz. The way you would access that is by hitting the function button, and then you can see that you can step in 1 megahertz increments and then hit the push to talk. And you can have a VFO-A is VHF, VFO-B is UHF, or vice versa. One feature the radio is capable of that I want to make mention of is that it will transmit on UHF while receiving at VHF and vice versa, meaning that it will work across cross bands, but it does not cross band repeat, and I want to make that clear. So for example here, our transmitting right now on UHF, test 1 2 3 4 5 5 4 3 2 1. And our radio is receiving on VHF.
Test 1 2 3 4 5 5 4 3 2 1.
There are a lot of capabilities within the radio. We're not going to go through all the menu functions and stuff like that. That would be a very long video. But one capability we will discuss is the ability to expand the transmit and receive of this radio just by entering a code on the keypad, along with a simple procedure. The radio as delivered only covers the 2 meter and 70 centimeter amateur bands as far as transmit is concerned, with an expanded receive capability in V and UHF. Now, in order to access the transmit capability of the VHF and UHF receive range for an emergency situation, what you would do is cycle the power off to the radio, depress your push to talk and your monitor button at the same time, and turn the radio on, and it says set reset. Enter in this code 3 2 4 0 6 6 6 5, and it resets itself, and now you have full transmit and receive outside of the 2 meter and 70 centimeter amateur band without affecting your memory settings, which is rather nice. To go ahead and reset and restrict the transmit to only the 2 meter and 70 centimeter amateur band, you would just reverse the process. Most users of this radio equipment are going to elect to use some kind of software solution to manage the memories in the radio. This is something that, in much older radios, we used to have to fat finger all of the frequency information in amateur equipment and then commit it to memory. Then they came up with alpha tags, and you could actually edit the alpha tags, but it was a somewhat clumsy process compared to just being able to do it now more like a commercial radio where you can go into it with software. Now, This software is the freely available one that's available for download, as I showed you earlier, from Yaesu. And it's a very basic program. It allows you to edit the memories, and it's a spreadsheet type of format, which is typical. It is only a 6-character display, so be cognizant of that when you're naming your channels. And then once you're done editing all of your stuff, you can just go ahead and program the radio by clicking right to radio, and it'll go right into the memory. And if we wanted to see what information was in the radio, we could just go ahead and read that information out of the radio, just like we wrote to it. And you can take these code plugs and take this one, for example, and shove this into another radio of the same type without any problem whatsoever. Building one of these cables is incredibly simple. The interface I cannibalized from a Baofeng Tech PC03 cable, and I had to build a test cable anyway for the portable radio so we can interface it to the service monitor to inject audio. And you only need 2 lines from the radio, and these are going to go to your 2.5 millimeter connection on the radio itself. To tie the interface into your radio, just run your ground line right to the sleeve of your 2.5 millimeter connector. You're going to take your ring side of the 2.5 millimeter connector, run it back to your receive connection on the interface, and then go ahead and get yourself a small signal diode or something of that nature. Don't try to use a power diode because there's too much voltage drop across a power diode. I tried to cannibalize one and it did not work out. But you're going to take and tie your anode into your receive line and your cathode into your transmit line. And that's all there is to it. Let's get started with our testing. First test we're going to conduct is current draw testing. At the top I've got a diagram of how I'm setting up the test equipment. When the radio is idle and not receiving a signal, the current kind of fluctuates a little bit. So what we'll do is we'll go ahead and go to our average. Our average is 53 milliamps. Current draw with our display on is 111 milliamps. Our current receiving, 50% volume, is 178 milliamps. Our current transmitting at VHF high power is 1.31 amps. Our current at medium power VHF transmitting, 877 milliamps. Our current transmitting at low power is 469 milliamps. Let's go ahead and begin our transmit testing. And the data we're going to collect from this are, first of all, frequency error. The radio itself is not going to transmit exactly on the frequency displayed. And typically, if you can keep that error less than 150 hertz in an analog radio, you're fine. Following that, we're going to test for RF power in both V and UHF at the high, medium, and low power settings. And then we're going to check for deviation for legacy wideband 25 kilohertz and narrowband 12.5 kilohertz. The equipment configuration is going to be as shown on the whiteboard for performing this test. On the left, you can see that the cable that we're going to utilize to take our audio frequency generator and deliver our 1 kilohertz 25 millivolt tone to the radio while it's transmitting for the purposes of deviation testing. We're going to use the sleeve is ground and the tip is your mic and push to talk line. The transceiver is going to be powered by its battery pack, and we're going to run that to the RF in port of the service monitor while the audio frequency generator portion of the service monitor is going to generate that tone, and then we're going to run it through a Motorola RTX 4005B interface box. The RTX 4005B is just a piece of legacy test equipment that's an interface between the radio under test and the testing equipment. And in this example here, we're taking our audio frequency generator from our service monitor and sending that AF signal into this port on top, and then through the circular connector and our test cable here, this plugs into the microphone port of the radio, and this allows the audio frequency signal to be injected into the radio while it's transmitting for the purposes of deviation testing. This is our VHF test at high power using 25 kilohertz FM. You can see our frequency error at the top there. So we're less than 20 hertz of frequency error, which is good. Our power output is 4.2 watts. and our deviation is 4.12 kilohertz. And this is our VHF test at high power using 12.5 kilohertz FM. So you can see our power is the same, frequency error hasn't changed, but our deviation has changed. And we're under 2.5 kilohertz of deviation, running 2.06 to 0.8 kilohertz. Here's our VHF test at medium power. This is VHF low power. UHF test at high power, 3.9 watts. UHF test at medium power, 2.17 watts. And UHF at low power, 0.45 watts. We're going to begin receive tests. We're going to capture data on sensitivity and selectivity. Sensitivity is most commonly measured in what's known as SINAD, which is signal to noise and distortion ratio. And when you see that 12 dB at 25 microvolts, that is typical measurement for LMR radio equipment. Just about every receiver you see spec'd out is going to have that measurement. And that means that intelligible speech will be present 12 dB above the noise floor, and typically the received signal that's coming into the receiver that produces that 12 dB above the noise floor is 0.25 microvolts. Equipment setup for this type of testing is extremely easy. You can see that we have our portable radio under test being powered by its battery pack. We have the antenna port of the radio hooked to the RF out of the service monitor, and then the AF in, or audio frequency in, is connected to our RTX 4005B, and that's connected to that 3.5 millimeter jack on the side of the portable radio. So it's really simple how this works. We're taking a very measured signal out of our service monitor, injecting it through the antenna port into our portable radio, and we're taking the audio and recovering the audio, bringing it out of the speaker microphone port, running it through our interface, and then from our interface it's going into the audio frequency input of the service monitor, which allows us to measure that signal. Here's our VHF receiver performance. 0.22 microvolts of RF is giving us 12 dB of SINAD, and this is what it sounds like. Here's our UHF receiver performance. We're getting 12 dB of SINAD at 0.22 microvolts, and this is what it sounds like. Receiver selectivity. The equipment setup for receiver selectivity testing is identical to just the receiver performance equipment setup. We just did our testing based upon comparing our radio under test, the FT-4X, with the performance of other contemporary radios. This is the ability of the receiver to resist extremely strong signals 12 and 25 kilohertz away from the tuned frequency. In a rural area where there's not much RF congestion, receiver selectivity isn't nearly as important as it is in a more urban environment which has a lot more radio frequency congestion. So the way this test is conducted is we start with our receiver tuned to a signal, in this case 146 megahertz, and we just have the squelch completely open, and we set the audio at the same level for each radio. So our open squelch noise floor, this is our SINAD reading. So we begin by generating a signal of minus 100 decibel milliwatts and tuning the signal generator 12.5 kilohertz off frequency. And then recording the results here of the SINAD reading. Next, we step 25 kilohertz away, and then we increase the power to minus 60 decibel milliwatts. So now that we understand how the test is conducted, we'll go over the results. The Yaesu FT-4X, which is the radio we're doing the video on today, and you can see the performance of it there. In just like the T70A and the XTS 5000, there was no signal present whatsoever at the 25 kilohertz level at that level of signal. At the 12.5 kilohertz level, you can see the performance of it and the Baofeng are almost identical when set for wideband, but when you set the radio for narrowband, it was completely quiet in the presence of those signals. Our final testing we're going to conduct is regarding spurious emissions and harmonics. It's not uncommon for radio transmitters to emanate signals outside of the desired fundamental frequency that they're operating on. Typically, these signals are minuscule. Now, harmonics are spurious emissions, but not all spurious emissions are harmonics. But harmonics are certainly the ones that we see the most of. A harmonic is based upon multiples of the frequency of operation or the fundamental frequency, typically doubling it. So at 146 megahertz, a harmonic would be 292 megahertz, and then 438 megahertz, and so on and so forth. Now, Part 97 rules have technical standards in place dealing with this, and I've got those listed on the whiteboard for you if you want to research that yourself. But the specific section that we're interested in for this type of testing is they must be 40 dB below the mean power of the fundamental emission. Now, these technical standards not only relate to equipment that you purchase, but also to equipment that you may build yourself, including amplifiers, etc. Those standards are fairly loose in comparison to standards in other radio services, such as Part 90. This is the way we set up the equipment to conduct this test. We take our transmitter or transceiver under test, put a battery pack on it, and power it, run a coaxial cable to this T here that's terminated at one end with a dummy load, and then has a minus 30 dB sample port. An inline attenuator is actually preferred for doing this kind of test, but I don't have a 30 dB inline attenuator. And then running a cable off of that port to the RF input of my Cellmaster set for spectrum analyzer. Our first radio we're going to test is not going to be our Yaesu. It's going to be the Baofeng BF F8HP. The reason why we're doing this is this is exactly the kind of results you do not want to see when you're performing this kind of test. And it clearly illustrates the relationship of harmonics to the fundamental frequency. This is at VHF high power. And you can see our fundamental frequency, and these are our harmonic spikes. And all of these harmonic spikes should be down below this line right here. Now that you've had a good illustration of what you do not want to see when you're doing this kind of testing, we're going to go ahead and test the Yaesu FT-4X at VHF high power. And this is exactly what you want to see. You've got your fundamental frequency, and you don't have any spikes above that line right there. Now moving along to UHF again, we're going to go ahead and show you exactly what you do not want to see when you're performing this kind of test, and we're going to be using the Baofeng BF F8HP at UHF on high power. And again, there's your harmonic spike. Now let's test our Yaesu FT-4X on UHF at high power. And we're looking really good. So what do I think about the Yaesu FT-4X? I think it's a good radio. I think that its performance is on par with any of the other inexpensive low-tier radios that I've come across. I feel like the radio's performance is on par with the higher tier models in the Yaesu product line. It just does not feature the same feature set that those higher tier radios have. The radio's accessorized with just what you need to operate. And for its price point, I don't think you can go wrong. It's $99.95 is what I paid for it. I've heard others that have paid $75 for it. So in this video, we've taken the radio, unboxed it, checked out all the accessories in detail. We've tested the radio. I've shown you just fundamentally how to operate the radio, explained how to build a programming cable, shown you where you can get your manual and your freely downloadable software from the factory to program the radio, how to utilize the unlock code to allow transmissions outside the 2 meter and 70 centimeter amateur bands, and learned a lot about the radio in the process. I hope this helps. This is Brett from SurvivalComms. Till next time.